Okay, so today we're going to be looking at the enthalpy, the internal energy. This is not new. And specific heats, CV and CP. Okay, so what's important here to understand is this, is that when we are dealing with closed systems, basically we have two possibilities. One would be a constant volume. The second one, if the piston is free to move, will be a constant pressure. Okay, this will be the closed system indicated by the dashed line. So from another video, it was derived, for example, that the amount of heat required to raise a fixed amount of mass by 1 degree is the definition of a specific value, and it was shown by experiment that the amount of heat for the fixed volume was equal to m c sub v delta T, and that the one for the piston was equal to Q equal to m c sub p delta T. Okay, so let's go a little bit back to this one, and let's say how would this fit within the first principle of thermodynamics. So if we use the first principle of thermodynamics notation, Q minus W equal to change in internal energy, that will give us, and in this case there is no work done, that gives us that Q equal to change in internal energy, but from here we know that this is also equal to mCV delta T. So basically we can conclude that the change in internal energy is equal to mc sub v delta T. So the important part over here is that you relate all the time the change in internal energy to the C sub v. So now if we do something similar for the constant pressure, what do we have? Q minus W equals to delta U. But this case, what do we have? Q will be equal to the change in internal energy plus work. Okay? And what is the definition of work using this sign convention is PdV. So basically we're going to have Q equal to okay, a little bit complicated here in notation. So let me just change here the delta U just for notation equal to du, so du plus P dV. Okay, and we know from the previous chapter that this is equal to mCp dt. So really we could say that Q, oh sorry, we could say that, yes, no, let's say that du plus P dV will be equal to m Cp delta T. Okay, So what is this new term over here? So let me just rewrite this one a bit different. So same thing we add here, delta U, let's call this one delta H, where H is what is defined as the enthalpy. Okay? So I'm just going to go now to this side of the page just to show something. So real definition of the enthalpy. This is the change in enthalpy over here, is internal energy plus work done by pressure. Okay? So this is the internal energy. And this term here will be the work done by pressure. And okay, work done by a constant pressure will be the more accurate definition. And let's see why. Because basically, I'm just going to do here the mathematics. We have H equal to U plus PV. What does that mean? Now, if we take the derivative, this will be equal to du plus P dV plus V dP. But you see, that's not the same expression that we had over there. Unless, what do we do? For P constant, what do you have? dP will be 0. So that will mean that we can cancel that term, and we'll have that dH, which is the same term we have over here, will be equal to du plus PdV. Okay, so what's important over here is that the same thing, you're going to remember that the change in internal energy is related to the C sub V. It's important that you recognize that the change in enthalpy will be related to the C sub P. Okay, and remember the enthalpy is the work done by is the internal energy plus the work done by the pressure. All right. Okay, next I'm going to prove this mathematically. So if you don't want to watch the rest of the video, it's completely fine. It might be too technical. Okay. So let's go back more to the fundamentals of thermodynamics. Basically, we say in thermodynamics that we deal with substances, and the substances are defined by the properties. So a substance can be water, helium, any gas, any liquid, or even a solid. And is defined by its properties. For example, you know that the properties of wood or a metal, or each metal will be different. Okay? So what happens is that the properties can also be in function of other properties. So for example, for the gases, you know actually the equation as the ideal gas relation, but that's what is known as an equation of state. Okay? Basically, you see over here that the different properties, P, V, and T and R, let's say, are constant. These three different properties over here: pressure, volume, and temperature. So let's say out of this function, you could say that if you want to find the pressure would be in function of what? and volume and temperature. Let's say you want to find the volume, you will say the volume will be in function of the pressure and the temperature. And if you want to find the temperature, you will say the temperature will be in function of the pressure and the volume. Okay? So basically we are not dealing with functions in function of one variable, we're dealing with function in function of two variables. So the same thing happened for the internal energy. So for the first case, if we deal with this case over here, constant volume for the closed system, let's say that in this case we say that the value of the internal energy will be in function of the temperature, okay, and the volume. Okay. So this will give us what? Now we have the function, then the total derivative du will be equal to what? So you have the two variables, so you first need to differentiate u, so you take the partial derivative. Let's say function first in function of t. So when you do that, you keep v constant dt. Then you take the partial derivative of u with respect to v, keeping t constant, and you have here dv. Okay, so if we use this relation to rewrite the first principle of thermodynamics equation, so neglecting the potential kinetic energy, we have this. In this case, there is no work, so this is 0. So what do we have? Q, okay, and this is basically the same thing as du. Q will be equal to what? Delta U, delta T, V equals C dt, plus delta U, delta V at T constant dV. Okay, actually if I do the correct definition, no, that's fine. So basically what happened? The volume is constant over here. So what do we have? This is 0, so these whole terms will cancel out. And we'll have what? Q equal to delta U, delta T, constant volume, dt. Okay? Or, now, I don't know if you remember, what was the equation we had for the specific value function of CV? Q will be equal to what? M C sub V dt, or you could use delta T. It will be the same thing. But just use this one to see you have the same thing. So in this case, really, if this is the energy, that one already includes the mass, but many times you will use the specific mass, the specific energy, which would be divided by mass. So in that case, you will have, so this time will be the lowercase u, not the uppercase. So here we have the m, v equal constant dt. Okay, and if you remember from this equation here, this will also be equal to du. So we cannot say that by looking at this expression, what Jules concluded is that the specific heat needed to be in function of what? Let's say 1 over m needed to be just in function of the temperature. All right. So basically, if you think about it here, we have u in function of temperature and volume, but when the volume is constant, that term disappears. So that will just tell that u will just be in function of t. And if you compare this equation to this equation, basically you will have that q equal to m Cv dt. So as before, as we did over here, from here you will find out that Cv is actually equal to what? Delta U delta T at constant volume, which is kind of similar to this equation here, okay, to this term over here.